So we've had a chance so far this semester to talk about the background of astronomy. You look up, you see stars, constellations, how these things get names, some of the motions in the sky, motions of the planets, and what people thought about this and how we developed modern understanding of the heavens, the beginnings of modern astronomy. And then we talked about how planetary systems form. We also talked about light and optics and how we know what we know. And to talk about how planetary systems form, what I did was at that point, I jumped later in the book and talked about asteroids and comets as a byproduct of the formation of the solar system. I think really that's a good place to do it. The reason the book puts that at the end of this first half of the book is that historically we knew very little about it, and so the normal order of these topics is background information and then the Earth as a planet, and then the other planets in order from the sun. And that's how it's normally done. Just historic, because we go, in that kind of fashion. What I did was I jumped to the comets and asteroids because I think they're a very important part of the solar system that is often overlooked. They're often stuck at the end of the semester. Very few people, get around to getting to them. And so in a lot of astronomy classes, they're very short-shifted. And so I want to make sure that we cover them. Now we're going to go back and follow pretty close to the order of the book. Go back to Earth, and then we'll talk about the Moon as our nearest neighbor in space. Then we go through the planets, Mercury, and then Venus, and Mars, Jupiter, Saturn, Uranus, and then Neptune. And about that point, we're at the end of the semester, and so we end the semester about that point. But the planet Earth, so not just the world we live on, but it is a planet. It fits into the solar system. And so we'll talk about interactions between Earth and everything else. I'll get back to talk about meteorite impacts and the effect that they've had on Earth. And we'll talk about solar terrestrial interactions, how the sun affects the Earth. So all that's going to be coming in this discussion about the planet Earth. We'll talk about changes in the planet, what it used to be, what it is now, what it's going to be. The Earth changes over time, as does everything, and so we're going to be talking about that as well. So this is our basic sort of order of topics discussing Earth and the planet that we live on. And so let's go ahead and get started now. So the planet Earth, we know a few things about it. It's 1 AU from the sun, basic physical parameters. You get this out of the textbook here. So it's 1 AU from the sun. The eccentricity is 0.017. That's not very eccentric. The Earth's orbit is very close to being circular. In fact, if you were to look at it from above, it would look very circular to you unless you actually took a ruler and measured across at different places and you realize, oh, wait, it's not quite a perfect circle. Orbital speed, average orbital speed is a little bit less than 30 kilometers per second. It's a little bit faster, a little bit slower, depending on which part of the orbit you're in. That's how fast we go around the sun. We already know the orbital period. How long does it take to go around the sun? The sidereal period, 365.256, almost 365.26 days. So just a little bit over 365 and a quarter days. That's how long it takes to actually go around the sun. The tropical period, the tropical year, is closer to 365.24. That's because the Earth changes the direction of its tilt ever so slightly every orbit around. And so the seasons repeat slightly less than 365 and a quarter. The actual time around the sun, slightly more, the seasons slightly less. And so the calendar is based on the seasons, not the actual orbital period. It's tilted about 23.5 degrees. Nutation changes that a little bit. The average density of the Earth, it's about about 5.5 grams per cubic centimeter. So density is mass divided by volume. So that turns out to be interesting. Okay. The other thing I want to point out here is albedo. The albedo is how reflective it is. Now that changes. The continents don't reflect as much light as the oceans do. Clouds reflect more light than the non-clouds. Okay. Ice reflects, snow reflects. So this is seasonal. You know, when we have a particularly snowy winter, we're reflecting more light. So that's how reflective it is. Average about 0.3. That means we reflect roughly a third of the light that hits us. About 30% of the light that comes from the sun reflects back off into space. It's not, the rest of it is absorbed. That's what's heating the Earth. If we increase the albedo, we reflect more light into space. If we decrease the albedo, we absorb more light. Now, this is one of the issues they talk about with climate change, is that if the Earth warms a little bit, the ice in the Arctic regions might melt. Well, if it melts, that means the albedo gets smaller, which means the Earth reflects less light into space, and that means it absorbs more heat and gets warmer even faster. Conversely, one possibility is that if the Earth is a little bit warmer, there's more evaporation and more clouds, which then makes the albedo go up, which reflects more light. And so it becomes a very complicated process. This is why we study the other worlds. Earth is very complicated. There's so many different factors that go into it, feedback systems that counter one another. And so we're trying to balance all this out. Average temperature at the surface of the Earth. Mean average temperature is about 57 degrees Fahrenheit. So that's the average across the entire planet. Now that ranges from the really hot deserts to the really cold Arctic regions. You know, but on average, it's about 57 degrees Fahrenheit. So that's the average. Okay. Obviously, the closer you are to the tropics, the warmer the average is going to be. But that's the global average. Okay, and then we have the atmospheric composition right there. Okay. Now, like I said, your book gives the average density as 5,500 kilograms per cubic meter. That works out to be 5.5 grams per cubic meter. I like to put it that way because in chemistry class, you often learn that water is 1 gram per cubic centimeter. But this is an interesting thing. If Earth averages about 5.5 grams per cubic centimeter, the two main types of rock that you find at the surface of the Earth are granite and basalt. Granite is about 2 3/4 grams per cubic centimeter. Basalt is a little over 3 grams per cubic centimeter. So, meaning if you had two rocks that are one's granite, one's basalt, the basalt one's going to be heavier. But if the rocks on Earth are about 3 and the Earth averages 5.5, what does that mean? What does average mean? Average is between the extremes, right? So average is well, basically average. I mean it is between the extremes. So the average has got to be between. So that means if the rocks that make up near the surface of the Earth are close to 3, the mantle is close to 3, that means deep on the inside has to be something a whole lot bigger than 3. And so this tells us the interior composition of the Earth has to be made of heavier stuff than what we see at the surface. And so what would that be? Well, turns out there's several possibilities. It could be all kind of different kind of things. But we can look at what's in the interstellar medium, the dust that's between the stars, the composition of that, and we find various kinds of things in there. We find, obviously, hydrogen, helium, most abundant things in the universe. We find oxygen. We find silicon. Well, silicon and oxygen are the main components of granite and basalt. Basalt has something else in it too. Basalt rocks tend to be a little bit dark because they also have a little bit of iron in them. And iron and nickel turn out to be another major thing that we find in the interstellar medium, another major thing that we find in meteorites. Okay, so this means that we have the idea that iron and rock are actually part of the Earth. The iron and nickel would be in the core. And so that suggests that since it's one of the more common things in the universe, that's going to be part of the composition of the Earth. And so the core is denser than the crust regions. This is a concept that your book refers to as differentiation. Differentiation means different parts of the Earth are different. Heavy stuff in the middle, light stuff on the outside. That's the sort of differentiation we have on Earth. Well, how does that happen? You know, if you have a heavy object sitting on a light object, it just stays there. The only way they can merge would be if they were liquid. Heavy stuff sinks to the bottom, light stuff floats to the top. They can go through each other. This suggests that when Earth first formed, it was molten throughout, and the heavy stuff sank to the middle, the light stuff to the outside. So the heaviest stuff, the iron and nickel, became the core. The heavy rocks, that became the mantle. The lighter rocks became the crust. So this is the sort of differentiation that occurred. It also means that other heavy things like uranium, thorium, other radioactive materials tended to sink because they're very heavy, even heavier than iron and nickel. They tended to sink to the core of the Earth, meaning there's a lot of radioactive material in the core of the Earth. That's actually heating the interior of the core, all this radioactive decay. So that's part of what keeps the core molten. Part of it is that it was so hot squeezed together to begin with. It was that heated up, and we trapped all this heat in there, and it takes a long time to get out. So there's multiple reasons the core is hot.